Okay, today is called Polynomials Day 2. But basically, I'm going to give you kind of a big review today of where we've been and what we have left. All right, I do not need you to know this format up here at the top, but I can tell you that that's basically about the remainder theorem, and that's basically about long division. So I know you know how to do 396 divided by 7 with long division, but I think it wouldn't hurt for you to practice. Put the 7, 396. Just take a moment. That'll review all the skills necessary to do long division with polynomials, another topic that's on the test. Okay, so take a moment and try 7 going into 396. I'll pause while you give that a shot. Okay, in case you got stuck, you should have been going 7 goes into 3. No, it doesn't. 7 goes into 39. Yeah, it does. Does it go in perfectly? No, but that's okay. So 7 times what would make something close to 39? 7 times 5 is 35. And notice then we put a little minus here. Don't forget that step. That's a critical step. Because when we do polynomial long division, you always got to put an opposite sign there. And that's a really common forgot thing. Commonly forgot. Anyway, this comes out to 4, and then the 6, and does 7 go into 46? Yeah, not perfectly, but what's the next one then? 7 times 6. 7 times 6 is 42. Notice I did this times this. On our polynomials, we'll have to do it times 2 things, but it's the same concept. And then there's 4 left. Now, here's the key. That's called the what? The remainder. Do you get if we have a remainder, then that means that we didn't have it go in perfectly. Okay, but do you remember me saying that what I wish they would have taught instead of remainder 4 is that that remainder could be written as a fraction. Okay, so I could say 56 and 4/7. Now, just for a moment, I want you to think, if I said 5.5, do you get that means 5.5? Do you get that means it's really 5 plus a half is what you're writing when you write 5.5? It's really 5 plus a half. It's certainly not 5 times a half. All right, 5.5 is 5.5, also known as 5 plus a half. So this is really 56 plus 4/7. That means 7 times 56 plus 4/7 would give you 396. Okay, so what do we do when we have a leftover in a polynomial? Let's say we have x squared. Let's start with a simple one that doesn't have a remainder. 6x plus 5. And let's say I tell you that you should check x plus 5 and see if that's a factor. By the way, if x plus 5 is a factor, what's a root? This is critical, that if I say -5, that's its root. If I say x plus 5, that's a factor. So I could say either one. I can give you this polynomial and say this is a root or this is a factor. And either way, you got to be able to set up the long division for it. Did you put an x up here first? It's a good way to start. I'll pause for a second while you do that. Recording going again. Okay, so we're putting an x first, and then we draw a line like this, opposite, opposite. And I have now x, and then there's not enough down there. Bring down the plus 5. And you're with me so far. And then this one makes it pretty obvious. What goes here? Although I suppose in a way, it's kind of like weird, but I need that to be replicated, so I need a 1 up there. Opposite, opposite, 0 left. Because there was a 0 remainder, it was simple. Okay? Now, x plus 5 and x plus 1 were the factors. So what were the roots? -5 and -1 were the roots. Okay. Now, this is an important one. On the polynomial remainder theorem, this is something that the ACT could ask you. How can I tell quickly whether 5, for instance, is a root of this? How could I tell if 5 was a root of this? Well, here's what you could do. If 5 is really a root, then x minus 5 will go into it, but that is not a quick little thing you could do. That's a long, painful process, right? What's a quick little thing you could do if 5's really going to be a root? The polynomial remainder theorem says that if 5 is really a root, then when I stick a 5 into the polynomial and I figure out if this is f of x, if I figure out f of 5, I stick 5 in, f of 5 has to equal 0. Can you just look at that quick and think about if you stuck in 5, do you think there's any chance this thing comes out to 0? You see how quick that is to check? So the ACT could ask you, given that, let's see, these are tough to formulate properly. How would they say it? They might say, what indicates that f of 5 is not a root? No, what would indicate that 5 is not a root? 5 is not a root. Well, you stick in f of 5, and obviously if I put a 5 in where all the x's are here, this couldn't possibly be a root. I'd like you to prove for me, on the other hand, that negative 5 is a root. Negative 5 is a root. Because if you stick negative 5 in, what happens? You have a remainder of what? 0. If you stick in a 5, it won't work. But negative 5, I may have screwed that up. Negative 5, did I say negative 5 or 5? Negative 5 is the one I want you to check, because I know 5 won't work. But negative 5, I'm 80% sure, works. Basically, if it's a root, when you stick it in, you won't have any remainder. You'll have 0. Well, I can just look at these last two and say they're going to cancel each other out, right? That's pretty easy. Then these two ought to cancel each other out. Let's find out if they do. This one comes out to negative 125, and this one comes out to 5 squared is 25. 25 times 5 is 125. They cancel each other out too. Look at that. So when I stuck negative 5 in, I got 0. F of negative 5 equaled 0. And you want the things that have a remainder of 0. All right, that's the thing I think you need to know for the ACT. Again, a typical question might be, let's say that they say f of 5 is 0, and here's your equation. Do you get by saying that f of 5 will equal 0, that I can put in a 5 here and here and here, and that this whole thing will have to equal 0? And do you get then I could solve it for n and figure out what n has to be to make that true? Because I'd have a number here. I'm not saying that I can make this one work, because honestly, I'm not sure if this one would work. But here's your process. I stick in 5, and then I solve it for n. In fact, yeah, I could make that work. There'd be a number I could put there that would make that work, would make it equal 0. Okay, so that's the polynomial remainder theorem. Next thing that I want to make sure that you have down, we talked about long division, is what if I gave you this equation? And I say y equals, or f of x equals, all that. Can you just tell me a bunch of things by looking at it? Can you tell me its right end value? Generally, is it going up or down? Can you tell me its left end value? Can you tell me where it hits the x-axis? Can you tell me where it bounces? Do you get what I'm saying? So if you can do all of that, you should be able to just kind of make a sketch of it and tell me what the thing looks like. I'd like you to try that next. Next thing I would ask is, there's a follow-up question besides the sketch, is what are its zeros, also known as its roots? What is the multiplicities? It's very easy. Multiplicities, if you just don't know that word yet, I'll explain it in a moment. The zeros and their multiplicities. And what is the degree of this polynomial? And on day one, I told you what would disqualify you from being a polynomial. This one is a polynomial. I just want you to remember what would cause something to not be a polynomial. I'll pause for a minute while you try to answer those questions. A sketch, tell me what the zeros and their multiplicities are, and what degree is this thing? I agree, it's bouncing at -5. But is it bouncing from the top or from the bottom? So you don't probably even want to answer that until we do the right end value. Is it going up or down on the right side? How do you know it's up? Here's how you know for sure it's going up. Because if you were to multiply this thing out, its lead coefficient would be an x to the third. There's a 1 right there. Probably should loop that in. X to the third, and it doesn't have a negative on it. That's the real key. If there had been a negative up front, that would have ended going down. But this one does not have a negative, and so therefore it is going up. That's why it's going up here. Okay, now at that 3, was it bouncing? No. And therefore it's just going through. Okay, and then how about at the -5? That it was bouncing, so that has to bounce here. And that implies it goes down at the end. What also, Miss R, would have told us that it was going to go down at the end? Do you know? Yes, you. I try not to say last names on the video. Why do I know this is going down? Other than the fact that it's bouncing, what else tells me that it has to be going down? All right. This odd power, the degree of it, is telling me that one ends up and one ends down, so therefore it has to be down. Excellent. Okay. So then, what are the zeros? These are the zeros. What are their multiplicities? That's this. So the zero called -5 has MPY, would be just a good abbreviation, so you don't have to spell out multiplicity. -5 has an MPY of 2, and 3 has a MPY, multiplicity, of 1. That guy. It's the power that they go to. And their degree. The degree of this thing was this thing that I multiplied out. It's a really good idea to take any polynomial, multiply it out, get its lead term. Because its lead term tells you so much. Since this was positive, I knew it was going up on the right. Since it was odd, I knew both ends must be going opposite directions. So its degree was degree 3. All right, here's another little bit tougher one like that. Oh, I'm going to throw an x squared in the front. Just an x. There's no minus anything. Hint, you could say it's x minus 0. It's the same exact thing as x, right? And I'm going to throw a negative. I'm going to put it in red so it's really clear. I'm not trying to cheat you here. What if that's -x? Whoa. What does that mean? All right, hint. You want to find the lead coefficient, something x to the 5th or whatever it is. And that'll tell you whether the right end is up or down, you know it touches at 3 spots. Boom, boom, boom. And I want to know what degree this thing is. I want its zeros and multiplicities. And I want you to sketch it. Pause, we give that a try. Okay, let's see how you did. I hope you caught. I made it red for Pete's sake. Should have noticed it. There was a negative in there. And that means when you multiply this out, this would be x squared. This would be another x to the 1. This would be negative x to the 1. And so that means it's x to the 4th, but it's got a negative in front of it. Its lead coefficient would be negative x to the 4th. That tells me two things. The negative in front tells me it's got to be going down on this side. The fact that this is an even number tells me it's going down on the other side also. All right, now I bet I fooled a few people on some of these roots. How many of you knew that that one meant it touched right there? Raise your hand if you knew that. Good. How many of you knew that this one touched at positive 3? Okay, good. And how many of you knew this one did not touch right there? What? Why wouldn't it touch at negative 7? Because what makes this equal to 0? Well, I got to solve this now. Because sometimes it'll be 7, sometimes it'll be negative 7. All right, let's find out whether it's negative 7 or 7. What is negative x plus 7 equal to 0? Do you get, if I put in negative 7 right here, it will not equal 0? So you got to solve that little equation. Just set this equal to 0 and solve it. Minus 7 minus 7, negative x is equal to negative 7, x equals positive 7. If I go back to the original, I put a positive 7 in there, do you get it will make it equal 0? So the roots are the things that make it equal 0. I know some of you are getting used to just going, oh, it's the opposite of whatever number's there. It's really what makes this equal 0. And 3 works on that one, but 7 is the one that works on this one. So this is not over here, it's over here. All right, it really tests whether you really know what's going on to throw in a negative in there, and that's why I wanted to do that today. All right, so now I know it's going down, and I know it's going to be a 1 right here, so it's a cut through, so it's going through that one. Another cut through at 3, because that's a power of 1, so it cuts through there. And then this means bounce at 0. If this gave you trouble, it's like x minus 0 or x plus 0 squared. And it's bouncing there, bounce, and then it goes down. There we go. One more thing, I can find out the y-intercept really easy. The y-intercept is where? What? X equals 0. And since, I'm going to clean this back up again. Since I put in x equals 0 right here, do you get it? It doesn't even matter what the other ones are. It's going to be 0 times whatever they are, which is 0. So my y-intercept's got to be 0, which makes sense from my drawing. So just don't forget you can check your y-intercepts that way. Okay, so we've covered a lot of stuff. I'm not going to try to cover everything today. I mean, the test isn't until Thursday or maybe Friday, depends on how things go. Next thing, I want to look at the homework problems that I'm going to give you for today. All right, so here's the last thing I need to teach you that I haven't yet. And that is, what if I just give you clues about it, and then you have to write a polynomial? What if I said, I told you that x equals 7 is a root, and it has a multiplicity 3. You can tell that's not an equation, but you could make one. Also, what if I said the lead coefficient is negative 6x to the 4th? Can you make me, there's a lot of different answers that would be right. Can you make me a polynomial that would be like that? Go ahead, try to design it right now. And as long as it does these two things, it has that for a root with multiplicity that, and it has a lead coefficient of that, then it'll be right. notice the lead coefficient can't just be the number you stick in the front. If it multiplies all the way out, then its lead coefficient is negative 6x to the fourth. So I hope you don't just go like this and then put some extra over here, because then when I multiply it out, the lead coefficient won't really be negative 6 to the fourth, because whatever's in here would make it get bigger. All right, I'm going to pause for a second while I let you think about that one and write down what you think it is. Okay, as soon as they said 7's a root, I can go x minus 7. You know what I'm saying? That's part of it. Now, how about its multiplicity? Where should I put that? Yes. Exponent on it. Good. Now, would this one, the way I have it written, have a lead term of negative 6x to the fourth? No. So what could I throw in so that it would, when it's multiplied out, have a lead coefficient of that? Somebody tell me how I can put something else on here to make that work. Come on, don't overthink this. It's not that hard. Negative 6 is close. Negative 6x is exactly right. Good job. There. Are there other ways to do it? Yeah. You actually could have put the negative 6 in a different spot. Like the negative 6 could have been at the end. I know it's a little weird, but you could have had this multiplied over here. As long as when it's all multiplied out, you get negative 6x to the fourth, you're okay. All right. What if I'd have said that this bounced instead of saying multiplicity 3? What if I said it was a bounce? What would that, how would that change your... How could you write it now? Actually, a couple things have to change. If it's a bounce, I think you know this is a 2 then, right? Why can't I just change that? Because now it's going to have a lead coefficient of negative 6x to the third. All right, so the simplest thing to do would just be to square that. Now it's going to have an x to the fourth. Or it doesn't say that there isn't another root. You know what I'm saying? I didn't break any rules. It's still going to have a lead coefficient of negative 6x to the fourth now. It just has an extra root. It didn't say that all of the roots are shown, so you could have done it that way. That one would have a lead coefficient of negative 6x to the fourth. And it would have a root at 7 that bounced. All right, so the main thing for today is just making equations that do what you want it to do. Okay, what if I said, oh, by the way, this, when it was all done, looked like this. How do I write the limit on the right-hand side? Do you remember talking about limits the other day? Lim of the function. It has to equal something. See if we can do it. The right limit and also do the left limit. Okay, this is one of those things where I don't want you to just stare at the board for too long if you forgot how this works. The limit of the function, the x always, until we teach you the more complicated ones, the x will always be approaching infinity or negative infinity. Because if you go way to the right, that's x is infinity. Okay, and if you were to do the other limit, it always says lim. It always says f of x. It always has an x going to. Those are things it always has to have. And it always has to have an equal. Every limit you ever write for the rest of your life will start this way. And all you got to do is fill in something here. Depends on if you're on the left end or the right end. And there are other kinds of limits too, but they always have this. They always have lim, f of x. They always have to have the x goes to. And they always have to have equal. And this is where the x thing goes. So logically, the y thing is always going to go on the after the equal sign. So what does it equal? Well, in this case, the limit of the function as I'm going to the right is this way forever will lead to this way forever, which is infinity. On the left end, as you can see, it's going down on the left-hand side. Synonymous with going down is negative infinity. This is a y value. And this course says x is going to. On the left end, what is x going to as I go to the left? X is going to negative infinity. How many of you feel like you could do that? I'm going to give you one more then. Let's see if you can do it. This one's a little weirder. I want you to write the left limit. I didn't write it over there. The left limit and the right limit for this. Notice that's an asymptote there. It's a strange looking function. There are functions that are kind of like that. We'll learn later this year. They have a cap on them. You get closer and closer to the cap, but you never actually can hit that cap. At a minimum, anybody should be able to tell me some things that are in my limit, because every limit has certain things in it. Row 5, person 2, that's you. Tell me something that's in my answer for the right-hand limit. Just tell me something to write for the right-hand limit. I'm just saying, even if you don't know anything else, you know limit. Good. And exactly. Perfect. And there's one more thing that has to be in every limit. An equal sign. All right. That's the framework. And then this particular function will have different things that go here and here. So what should we put for this particular function? J. Tell me, right end. The right end is going this way. Just tell me something you know about x. Yes, and so it's going to keep going until you hit x is going this way, x is going to infinity. All right? If on the right-hand side, you just want to memorize that x goes to infinity on the right-hand side, you could do that. And then conversely, on the left-hand side, it's going this way. I'm going to give you a second shot at this one. What would x have to be over here? Tell me what to write to start with on this limit. You got it. Good. Now, I only need my y values now. If I go way, way, way this way, how high, which is what y means, how high will it be if I go forever that way? Well, it can't be 0, but the limit approaches 0, so we say it'll hit 0. It'll hit 0 about the same time as you hit infinity. And you'll never hit infinity. And also never actually hit 0. Right? Think about this. Limits are talking about like forever. It's a concept. Like infinity. You can't get to infinity, but you can get infinitely close to infinity, and then I'll get infinitely close to 0. It won't actually hit 0, but it'll be as close as it can possibly be to 0. Okay, so anyway, this one on the left end, as I go forever this way, and then it's just the y value. Generally, is it going up to positive infinity? No, it's going down to negative infinity. How many of you had negative infinity right there? Okay, good. All right. One more with limits. You know this function. It's the 1 over x function. What's the right end limit? The right end limit. I'd like you to compare it with the kid next to you that I always pair you with, rows 1 and 2, rows 3 and 4, rows 5 and 6. See if you get the same thing for your right end limit. Okay, I wrote it in red there, except I didn't finish it. But that's what you'd write for every single limit you ever write. And now, if it's the right end, x was approaching infinity. And as you get infinitely far that way, what's the height of the function when I get way over there? The height is 0, and therefore it's 0. Your homework is, you may want to watch this part, sit down, because otherwise you'll have to do all of them. I think it's worth your minute here. I want you to do all of this page. You should be able to do all of those. And you may skip number 5, and you should do number 9. So just the first page plus number 9. That's all you got for homework. Get it done.